Hello, everyone, and welcome back to another episode of the Science Podcast by Science Society Club. I'm Noat, and this is Justin. Today, we're going to be talking about something that's very sciencey and mathy, but we're going to try to simplify it somewhat.
Yeah.
And we're also going to try to limit this episode down to evaluating expressions and like some simulation stuff using numerical methods so that no one go insane.
Yeah. So, as Noat mentioned, today we're going to be talking about a field of mathematics known as numerical methods. So, usually when we approach problems in mathematics, there are two ways of doing things, analytically and numerically. So, doing things analytically is always good, and it's a good thing to know how to do. But sometimes when things get crazy, we want to bring computers into the mix and do things numerically.
Yeah. So, first, we're going to start with a very important thing in math, doing calculations or computations. So this portion is going to be very useful for a lot of people in science majors. It's going to simplify your life, especially for those who study calculus.
Yeah.
So the idea behind numerical computations or numerical methods is that instead of getting some sort of exact value like pi or square root of 5, you're going to approximate it to some acceptable error bound. So what it means is that you can think about how we really do math in real life. We approximate things anyway. So for example, pi is approximated to 3.1415, whatever the rest is. I don't remember. But as long as your approximation is not horrible, like making pi equals to 3 or 4, like some certain field of study, it will be fine. I will still like you. Anyway, so in order to illustrate this, consider this integral of 1 over 1 plus sine x dx. Some of you may start crying now, but that's okay. We're here to help you. So suppose you're a Calculus 1 student. You know what an integral is, but you don't. Whoa! So you're a Cal 1 student. You know what an integral is, but you don't really know the tricks to necessarily solve this.
Yeah.
So an informal definition of an integral is to find the area under the curve, and then you can cut the area under the curve, or whatever shape is under the curve, into very small pieces with some width, and then as that width goes to 0, you will get infinitely many pieces, and then you sum them all up. The idea behind analytic methods is that you solve it by hand. So a way to solve this integral in particular is you multiply it by its conjugate, you use some trig identity, and you evaluate the integral. But it's very involved, and the answer that you get at the end, tan x minus secant of x plus some constant, it's still in the form of trigonometric function.
Yeah.
And if you're going to find this integral for the range of 0 to 1, it's a lot more involved to compute trig functions that does not have a pi value in it.
Yeah. Like what's the cosine of 1 and...
I don't know.
Yeah.
So you're going to end up using a calculator and approximating your answer anyway. So at the end, you're not going to get a human interpretable answer, and you're going to approximate.
Yeah. So here's a potentially simpler solution, right? So as Nawat mentioned earlier, we can think of an integral as the area under the curve of the function. And what we want to do is to approximate this area. Analytically, what we do is we cut it up into little chunks, right? Little small trapezoids, right? And then as the size of those sort of gets smaller and smaller and smaller, approaching infinity, we can find the area. But we can use the same concept numerically, but instead of summing up, infinitely many pieces, which will take forever, you don't want to do, right?
Yeah.
We can take the area under the curve and cut it into small trapezoids, the size of which we can sort of tweak, right? So
Just make it very small.
Yeah, preferably smaller is better, but too small is not
going to
good.
take forever as well.
But then once you do that, all you have to do is calculate the area of each trapezoid, right? Sum them up. And this is very easy to compute. It's at most, like 5 lines in Python. Yeah. And doing so will give you an approximation of the integral, the definite integral in this case.
And as the width, the size go down, then it will get very close to the actual value.
Yeah. In fact, so close, you probably won't care about like the error.
I don't know, the thing after the 20th
Yeah.
decimal place.
Yeah. So like why does this matter? Why exactly do we care? Well, even though this integral we showed you looked kind of nasty, it is still a nice integral. And then a lot of, a lot of expressions you see in calculus courses do have sort of like nice forms because, you're still a student, right? And you can sort of work them out into nice answers. Yeah. But most integrals in real life do not look as nice as this and have answers that do not look that good as well. And technology exists, so why not use it, right? Yeah, so for other computations, you can pretty much use a similar approach by sort of looking at the formulation of the problem, going back to simple principles, and then finding out how to compute it computationally or numerically. Yeah.
And at the end, as we've mentioned before, as long as you don't make a bad approximation, like making pi equals to 3, no one's going to care. No one's going to cry. Anyway, that's one thing that we can do with numerical methods. But the problem is a computer doesn't really know what a cost function is, a cosine or a sine, or generally any trigonometric function.
Yeah, like there's no sine chip in your computer.
Yeah. I don't even know how to compute a sine by hand. So in order to do that, we're going to use some calculus trick. So this is sort of where the useful analytical stuff comes in. So we're going to use a trick called Taylor's series expansion. This is something that you may learn in Cal 2 if you ever take it.
Yeah.
So it's going to be a bit more involved than the last portion because now you need to know how to differentiate. So here is what a Taylor series expansion is going to look like formally, but the quick explanation is that you take differentiation. If you take enough differentiations of the complicated function, you can convert that function into a polynomial, which is something that a computer knows how to calculate. Because a computer knows how to square some value, but it doesn't know how to find the cosine of that value. So it's basically converting something that's complicated into something that a computer can compute. Yeah. But unfortunately, you still need to know calculus and how to do differentiation with a Taylor series expansion. So this is more like a demystification of the dark arts behind the calculators that we use nowadays.
Yeah, so I feel like it's kind of cool to know because in Cal 2, like you do see Taylor series, but you're not quite sure what they're used for. But then now you know, like,
yay! It's actually realistic. You actually use it in real life.
Yeah. So next time you calculate sine on your calculator,
you'll be like, I know where that came from.
Okay. So moving on, right? So far we've been looking at what expressions involving what integrals or derivatives or calculating some value. But what if we wanted to try solving equations? For example, if we have some function, fx equal to something, right? For example, right, let's go with an example of sine x equals to x, i.e. we would like to find some value of x such that the value of its sine is equal to itself. Yeah. Now, what we can do, like if you wanted to try doing this analytically, right? Okay, you could take the...
You can start by crying.
No, you could take the inverse sine, right? To get rid of the sine on one side, right?
But what is the inverse?
But what you'll find happening is that, okay, instead of sine x equals x, now we have x equals the inverse sine of x. Same problem, right? Okay, but luckily we can solve this numerically. Now there's a little trick, right, which you can have up your sleeve, which is any single function, right, or equation can be massaged or turned into the form something equals to 0. For example, in this case, sine x equals x, you just move x over from the right-hand side, right? Sine x minus x equals to 0. It's the same thing, right? Now what we want to do now is find some value of x such that if we plug it in, right, sine x minus x is equal to 0. And we can tell that to a computer, right? Using this one algorithm known as Newton's method, right? We can specify some guess. For example, it might start at, I don't know, 1, 10.
Yeah, you can start
wherever,
one
right?
Is a good choice.
And then we will tell the computer to try to take this guess, plug it in, right? And if it's equal to 0, great. If not, using this update rule, right, Newton's method, right, we can take our guess and improve it. Like we do that again and again and again until we have a solution, right? This is known as root finding. Yeah. Okay, so why exactly does this matter? Well, we're often faced with a lot of problems like these, right? And instead of trying to learn how to sort of massage these weird, complicated math expressions, right, we can learn how to sort of fit things into solvers instead. Not exactly solving it by hand, but transforming problems into things that computers can do for us. Which, like, we have computers and they are powerful. Why not let them do it for us?
Yep, and I have a good news for you. Computers can do a lot of things. I love them so much. Anyway, so a lot of these things as we've mentioned, so integration, differentiation, Taylor series, or like a lot of the trig functions, they are mostly implemented for most people. So if you use a language like Python or Java or like some of the popular languages, most of these things are already going to be implemented for you.
Yeah, they have libraries.
Yep.
Right.
So in Python, you can use NumPy, you can use SciPy, you can use anything that ends with a pi. Too many of them. But the good thing is that these are already implemented, and you can just write up some very short code to compute these things. But the bad news is that you still need to know a little bit of theory if you want to write these from scratch. For example, with Taylor series expansion, you still need to know how to differentiate to approximate a given function or something like that. So you end up needing that theory that could be very complicated, especially when it comes to something like statistics or probability. In statistics, there are a lot of formulas, and sometimes it's very hard to grasp the idea behind each formula or each method. So we can also bring computers to make it more understandable, or maybe do things that would be basically impossible analytically.
Yeah. So statistics and probability by themselves are really useful things to know, right? If anything is applicable to like everyday life, it's definitely those two fields, right? They're really useful. But a lot of times, right, there are questions that are quite hard to answer analytically. Like if you're doing probability and you want to wonder, if I flip a coin, what's the probability of me getting heads, right? Of course, that's fairly straightforward. But for example, if you wanted to find out if you and your friend each had 2 dice, you rolled it, you took the product of the results, and you compared with your friend, what would the probability be of you getting the same value as your friend, right? Doing this analytically is a nightmare, basically. Yeah. But luckily,
we have computers. The thing that I love more than human. I mean, I'm joking, definitely. Anyway, so because we have computers, and computers are very powerful at repeating the same task. So what we can do is we can write a very short program to simulate the game that you're playing with your friend. So you can simulate you and your friend rolling 2 dice, and then make it finding the product, and then you can repeat this simulation many, many times. Maybe in thousands, in millions times. And in the end, you're going to get a pretty good approximation of the actual probability of you actually getting the same score as your friend. And there's probably a theorem out there for statistics people.
The law of large numbers.
Yeah. But in general, the more simulations that we do, the more accurate that we get. And this can be used for other things that is a bit more complicated than a simple game of rolling dice like blackjack. And because we already know that computers are pretty good at repeating the same task over and over again, we can also apply it to another silly but clever thing that we all love.
So for the final topic today, we're going to be talking about one of our favorite algorithms, which sounds really dumb, but is also really useful. Right? And the way it was introduced to us was with the following example. So suppose we were given 500 points scattered on an axis, and these would be like XY coordinates, right, scattered on a plane. So how might we find a triangle, right, if we choose 3 points out of these 500 with the largest possible area? In other terms, like, how do we just basically create a triangle with the points given that has the max possible area out of like all possible 3-point combinations? Yeah? So we could try all the combinations. Like, why not, right? We have computers, they're pretty good at calculating stuff, and with modern computers you can run things really fast. However, in this case, with 500 points, that would be 500 cubed, possible combinations of triads, right? which would be
Very
a pretty
big.
big number, right? A lot of different combinations to try, even if it guarantees the best possible answer. And plus, if we had a number of points that was greater than 500, like 1,000, 10,000, we might be waiting for the rest of our lives for it
You're
to
going to
run.
die before the thing finds the actual
Yeah.
answer.
So luckily, we can do something much dumber. Just pick random points and change them randomly.
Mm.
And if we make a change that increases the area, we hold on to it. And if it doesn't, we throw it away. Yeah. So to sort of like explain more in depth for this example a bit, what we basically want to do is to pick 3 points out of the 500 at random initially as our start, right? Then we would compute the area for that as our baseline. Then what you want to do is you change one of them to some other random point out of the 500. And if doing that change increases the area, then you just save those new points, right? And if it doesn't, you just forget about it and do it again and again and again and again. And if you repeat this process about, I think, 20,000 times in this instance, it is enough to obtain the best possible answer. Yeah.
And this can be generalized to use on a lot of other things. So an example that we just gave is an example of an optimization problem. Sometimes the optimization solver that we have cannot solve discrete, but that's a whole nother thing. But there are some sort of problems that a general solver cannot solve for now. So you have to make your own thing. Other than optimization, you can use it to solve scheduling problem. You can use it to crack substitution ciphers, become hackerman, which is something that all of us want to be. And it can also be used to approximate a pretty good answer for a very popular problem in computer science, which is called the traveling salesman, where you are given a bunch of locations and you want to find a path that gives you the shortest distance. So in this case, it's not going to give you the exact best. It's out there, but it may not be the best out of every possible one, but it's going to be close enough to the best that you're not going to care about whatever the margin is.
Yeah. So, yeah, hill climbing, it sounds dumb, but it's actually pretty good. And we have to stress on like pretty good because it isn't perfect. It's not a magic algorithm that can solve any single problem that you throw at it. Because, as Nawat said, you get an approximation. It is a random algorithm that is not guaranteed to give you the same answer every time. In this case, we call it non-deterministic. And sometimes we do want to have a little more certainty in our answer, right, rather than an approximation. But if you want to learn about that stuff, go take algorithms.
Which is another beast on its own. Anyway, so that is pretty much it for the content part of this episode. So now we're going to sort of start a discussion on what should schools teach to students. So nowadays, the things that are taught in school, especially for calculus, is usually how to solve equations or evaluate expressions using analytical methods. But sometimes these ways of solving problems are not the most realistic way, because as we've mentioned before, it's not the integrals that we see in class are usually simple ones. So what do you think? Should we change the things that we teach in schools or universities?
Well, I'm sort of conflicted about this because I do think that while sometimes the analytic approach may not be the most intuitive, it is sort of useful to sort of, like, I guess, or I want to say, like, you agree. It is sort of useful to lay the foundation for our understanding before moving on to something higher level. Like, you have to be able to walk before you can run, right? Yeah.
Yeah, and I agree with that because I feel like even if you know the numerical methods, knowing some analytical tricks will help you. At least sometimes you will be able to simplify. If you have an integral that is very clear to you that you can turn it into something that's a bit more cheap to compute, then it's definitely better to make it to take the cheapest version.
Yeah.
Because obviously, even if as powerful as computers are nowadays, it still has its own limitations. And if we really want to minimize the cost, whether it be electricity or time, you're going to want to run your computer for less amount of time, and the cheaper computation can help with that.
Yeah. So it's basically less about just like, you wouldn't want to only teach numerical methods, right?
Yeah.
Because then it would to me, I think it would just involve sort of throwing stuff to your computer and having it solve it without understanding what's going on. Sort of like black magic, which is not what should happen. It should be like, you know what's going on and you know how to solve it.
But you're getting a helper.
But you're getting a helper, right?
Yeah.
You're saving your time, right? Yeah. But I do think that having numerical methods being taught does sort of give a more intuitive approach to understanding how a lot of things work.
And I think it's a bit more realistic for people who actually want to work in fields that involves numbers.
Yeah,
So
statistics.
Yep. So at the end of the day, it's probably going to be best to mix analytical and numerical things, but I don't know. Maybe you disagree. So you can let us know in the AT forums or in the comments if somehow you stumbled upon this video.
Yeah.
Anyway, that is it for this episode, and we will see you next time whenever that comes out. Bye-bye.
Bye.